Good afternoon, everyone. I'm Olivia, and I'm from the Department of Mathematics, and I'm a second year student here at IIT Delhi. So, on behalf of Indian Institute of Technology, Delhi, it is my great pleasure to welcome you all to the inaugural talk in the ANRF Plus IIT Delhi Seminar Series. We are delighted to see you all here, and um, and here today we promise an intellectually enriching session. To formally introduce the ANRF plus IIT Delhi seminar, I now invite Professor Ashwini K. Agrawal, who is the Dean of Research and Development at IIT Delhi, to address the gathering.
Welcome to IIT Delhi, and thank you for initiating something which is going to be a remarkable journey for all of us. So this is termed as ANRF plus IIT Delhi. So it's a combined initiative of Anusandhan Research Foundation, National Research Foundation, which is the funding body for basic research, fundamental research, and applied research to various institutions in India. So it is their initiative to create awareness about the science and engineering research which is going on in various institutions as well as abroad, and to bring it to the audience everywhere. So this initiative is aimed at disseminating the information which we generate. So as you all know, institutions like IIT Delhi and others, they are there to not only teach, but also to generate information. And once the information is created, it needs to be discussed. So we have seminars, conferences, and things like that, and obviously publications to do that. But a face-to-face discussion in an informal or a semi-formal manner is something which is very interesting, very important, so that students can ask questions directly without even going to one particular conference or the other. Bringing the people who have generated something important to the institute, to the public, to the student body at large is a very important step. So I'm very happy that this series has been initiated with the initiative of not only just ANRF, but our Dean ODI and their team who have put this thing together. And we are going to see a lot of such series in the future, such talks and seminars in future. Professor Atish Dabholkar is a known figure, and I was just reading about him a little bit. Things like string theory, etc. I think a formal introduction would happen, but these are the things which have been fascinating me as well, though I am a textile person. So for us, strings are fibers. And but yes, I think somewhere everything falls into some kind of a structure which is very unique, and we are all trying to understand that. So I'm really looking forward to his presentation and his lecture and share his knowledge which he has generated. I'm very, very happy that he's here. About IIT Delhi, well, it's an institution which was established almost in 1961. That is when we started. 64, 65 is when research and PhD, etc. Started happening and people started coming out. We have today 65,000 alumni base, which is spread over the entire world, right? So Professor Atish comes from, I think, IIT Kanpur. So as IIT Delhi, IIT Kanpur is also one of the leading institutions. Actually, 5 original IITs, for those who are new maybe to the IIT system, RIT, Kharagpur, Madras, Bombay, Kanpur, and Delhi. So these first 5 IITs were established long back. And since then, we have been able to generate a reputation through our students, through our faculty, of doing something special for the country and for the world. We may not have reached the top of the international community, but we are very near. We are number 26 in science and engineering, which is a feat in itself. With the kind of facilities we have in India, it is probably one of the best. But if we compare it to the rest of the world, we may not be spending as much. as other universities abroad do. So looking at the per dollar output, IIT Delhi, IIT Kanpur, etc., everyone, all the 5 IITs probably are among the top in the world. This I'm saying you because with limited resources, what this community has been able to do is wonderful. And I'm very proud of that. Today, we are going to see one such person who has made remark and who has come to the top and trying to create international impact. And it is a real proud moment for us to hear him, all this, what he has to say today. IIT Delhi has almost 31 academic units spread over all kinds of specialities. And Department of Physics is one of the important departments, which is also running an undergraduate program in applied physics, which is engineering physics. So are there people from just physics or other backgrounds also? One or two or more? I think many are there. And I think a lot of students are also there. And I'm definitely a one which is a non-physics person, so we'll be listening to the talk. IIT Delhi has been changing, and just a little bit of a direction which we have taken. Mostly we were initially seen as the undergraduate institution with a lot of undergraduate teaching, and our undergraduate program, as you know, is highly competitive. Slowly we have moved to postgraduate, and today we have more postgraduate students on campus than undergraduate. We have almost 13,000 plus students, and we have slowly transformed from just the teaching, undergraduate teaching institution to someone which is teaching as well as doing research. So almost with 3,600 PhD students, we are spread across all kinds of faculties in all kinds of areas which are of uniqueness to IIT Delhi and other such institutions. We have lately looked at taking our innovations or our research into more translational world. And that is the change which we are doing with a mind so that IITs are also known for taking something to the society which can be used directly by the society. So all three aspects, teaching, fundamental research, and applied research, is what we have now entered into lately. And I think all our schemes are now targeted to bring this aspect up and up. So thank you very much for giving me this opportunity of welcoming you and initiating this series. And let's hope to hear such more in future. Thank you very much.
Thank you, Professor Agrawal, for outlining the purpose and aspirations of this initiative. And we look forward to many more engagements in this series. I guess we all are very excited to hear the talk. But before that, I would like to invite Dr. Shiv Kumar Kalyan Raman, who is the CEO of ANRF. He would be going to speak about the broader vision of this collaboration and the role of ANRF in strengthening the research partnerships here at IIT Delhi. May I request you to kindly address the audience?
Thank you. Like any other bureaucrat, I'm fashionably late. I'm really sorry for the delay. But it's wonderful to see the ANRF+IIT Delhi Seminar Series being kicked off with this inaugural talk by Professor Atish Dabholkar. And just wanted to give you some idea of why we are doing this sort of series. First, we like both great talks as well as sort of webinars and other sort of things to be much more widely disseminated within India. And we want to use, individual institutions to take leadership, as well as ANRF will be amplifying this as part of our platforms as well. So all the recordings from all the talks in IIT Delhi, as well as ANRF Plus is a program we're doing with select institutions across the country. And all these talks will be also hosted on our ANRF YouTube channel, and we'll be actively promoting it as well. So this is part of our goal of using the social media as a means for disseminating science, as a means of celebrating research, and also making research cool again as well in India, I hope, and part of building a deeper research culture and so on. So I don't want to take any further time, and would like to first congratulate IIT Delhi for actually taking the bait and joining hands with us, and we are delighted that we can do this. Thank you so much.
Thank you for those insightful remarks and for highlighting the importance of such research collaborations. It is now my privilege to invite Professor Abhishek M. Iyer from the Department of Physics to introduce our distinguished speaker for today's seminar.
Good evening, everyone. Thank you, Olivia. As Professor Agrawal said, Professor Dabholkar doesn't need any introduction, but it is my honor to introduce him to this audience today. Professor Dabholkar is the director of ICTP, the International Center for Theoretical Physics, with the rank of Assistant Director General at UNESCO. So he is well known for his research in string theory and quantum black holes, much of which is built on the foundations laid down by Abdus Salam on his work related to unification of forces. And Abdus Salam is the founder of ICTP. So Atish completed his undergraduate education at IIT Kanpur, following which he moved to Princeton for his PhD, and then he spent postdoctoral positions at, I think, Caltech. Then there was Rutgers, before he joined TIFR. He was there in Tata Institute of Fundamental Research, Mumbai, until 2010, after which he moved to Sorbonne. And he has been in ICTP since 2014. Now, Professor Dabholkar has received many awards. One of them is the Shanti Swarup Bhatnagar Award in 2006 for his outstanding contributions for establishing how quantum theory modifies the entropy of black holes, and his pioneering studies of supersymmetric solitons in string theory. Among his other honors include the Chair the Oxylons from the ANR, and he's also an elected fellow of the Third World Academy of Sciences. So I'm very happy to have introduced Professor Dabholkar, and I hand over the stage to Olivia.
Thank you so much for the introduction. And now I guess the audience is waiting for Professor Atish Dabholkar to address his talk. So may I please request you to come on stage.
Okay, so first of all, thank you very much for this wonderful opportunity. It's a real pleasure for me because I also an IIT alumnus. So it's a great pleasure. IIT Delhi is, of course, as was mentioned, is a part of the IIT system, and it's really great to be back. I've never been to IIT Delhi before, but many of my close friends and colleagues who are in the audience from IIT Kanpur are here as faculty members. So it's a pleasure to be here. I also had the pleasure of meeting Dr. Shiv Kumar last year, and it's a great initiative of the Indian government to support science in the 21st century with this new initiative of ANRF. So I'm honored that to be the inaugural speaker for this very nice initiative. And I think my today's talk is perhaps touches both these themes. So I'm going to crisscross between these two themes. So as you can see, Abdus Salam is shown here. He was a Nobel laureate who got the Nobel Prize in 1979, founding director of ICTP, which is now known as Abdus Salam International Center for Theoretical Physics. So it's particularly, again, very nice coincidence that it happens as this is also Abdus Salam 100th year, centennial year. And keeping in line with ICTP's mission and Salam's own aspirations and also my own thinking about this, I have decided to divide this talk into two parts. It will be sort of crisscross between two themes. One is this quest for unification of all fundamental forces, which has been a very exciting endeavor over the past century, or even more, and ICTP's unique mission to unite the world through science. And this is something that is, again, related to the notion, the mission of ANRF and also of IIT Delhi. So I want to now start my first part. I will go back and forth. I will first talk about the idea of unification, starting really at the very beginning, since not everybody here is a physicist. Then I will switch to the idea of joining forces to unite the world. And then I will go back again to unification, and then I'll come back again. Basically, I will talk about the past of unification and past of ICTP first, and then I will talk about the future of unification and future of ICTP next. So the most, all of you are probably familiar with this most important unification, is the unification between electricity and magnetism, joining electricity and magnetism. So here is electricity, and here is magnetism. Two completely different phenomena. They don't seem to have absolutely anything to do with each other. But these drastically different physical phenomena are actually but two sides of the same coin, and in a very precise way. So we now think of it as a diverse manifestations of a single whole, some unified structure. And this is what is meant by unification. This is how the word unification is used. Sorry, what happened? Okay. Unification means you try to understand diverse phenomena as part of the same thing. So they are joined together at a deeper level, even though they look very different superficially. So this is, you can call electromagnetic unification. So you know that electric charge creates an electric field. But if a charge is moving, then it's electric current. And you know that electric wire generates magnetic field. So therefore, it's kind of natural to expect that magnetism is electricity in motion. And this, in fact, became the foundation of special theory of relativity. But this is what was made precise, actually, in 1860 by Maxwell. This is Maxwell, one of the great physicists of all time. And he introduced these two very simple equations. Okay, I have simplified. You have seen Gauss' law, Ampere's law. It's all sitting there in this very nice unified framework where there is one single electromagnetic field, F. The electric field and the magnetic field, which you normally remember, you write as E and B. They are all combined into a single field. And these are known as Maxwell equations. And sorry, and J is the current which we talked about. So unification of electricity and electromagnetism was already achieved, but very surprisingly, and this is one of the great discoveries of physics, it turned out to be unified with light. So this is electricity, this is magnetism, but the equations that Maxwell wrote down turned out to have wave-like solutions, where the magnetic field is oscillating this way, electric field is oscillating that way. There could be no charge, but they're supporting each other, and the wave is propagating this way. And amazingly, the speed of that wave is finite, and it is the speed of light. So suddenly, out of the blue, in a way, we got light. So basically, electricity, magnetism, and light are three sides of the same coin. And this is perhaps the most spectacular example of unifications which has had enormous implications in all our lives, including the mobile phone or this presentation. It all depends on these beautiful equations that Maxwell wrote down. Very simple equations you can write in one line, but it contains all the technology. Really, I really mean all the technology that has to do with communication, light rays, X-rays, everything that has to do with light is contained in those equations. So that is the kind of power of unification. And before we move on, we have to remember also that we were talking about a classical electromagnetic field. But as you know, you have things like laser, which you cannot understand in a classical language. And photon is the quantum of light. And when you have lots of photons, it looks like a classical electromagnetic wave. But this classical electrodynamics is an approximation of a more correct, more complete theory, and that is known as quantum electrodynamics. And this theory has been so spectacularly successful. I'm just giving you one example of a quantity which has been computed using theory and experiment. And you can see you have to keep going down the digits before we see any difference. So this is again a very beautiful, delicate experiments and very beautiful and delicate theory is needed to get this agreement. So far, electricity, magnetism, light has been unified. So we are happy. But people discovered that actually there is something called the nucleus and there was radioactivity. So when Rutherford discovered that there is a nucleus, this is Rutherford. It's actually a very simple experiment he did. He took a gold foil and shot some alpha rays at it. And I have seen that original experiment at CERN. It's a small one. But that philosophy became the philosophy of particle physics for the next 100 years. This is how we actually now look inside matter. It's a bit like you want to learn how a car is made up of. So you take two cars and you collide them and bang them against each other. And you study what comes out, and you see a steering wheel that is coming out flying. Then you figure out, oh, there is a steering wheel, and then you say that there are brakes. So this is a very primitive method, but that's the method particle physicists follow even today. But Rutherford's discovery was something very dramatic for his time, because he was expecting when he shot these alpha rays, they will he was imagining the charge is like a fuzzy cloud. But instead, it is concentrated at this extremely tiny nucleus, 1,000 times smaller than the size of the atom, or even more. So it was like most of the time, the array, nothing was happening. Once in a while, suddenly it will come bang at you. This is known as the Rutherford scattering. And he was very surprised by this. And that led to this solar model of the atom and so on and so on. We now study, we do this in high school now, that the nucleus is made up of protons and neutrons and the electron is going around. But now, starting with this simple, nice, beautiful and major experiment of Rutherford, we now have 23 kilometer, many kilometer long accelerator to do basically the same thing. You take two cars and bang them against each other. You take two protons and bang them against each other and try to study the structure inside. And the size of the detectors, this is the detector. You can see there is a human being standing here. This is how enormous the detector is. With extreme precision, people are now able to measure what is happening inside the nucleus. And India is part of these experimental programs. But now we have two new forces. There is a weak, strong nuclear force, which keeps the nucleus together. And there is also radioactivity, which was discovered earlier by several people, which is responsible for the decay of the nucleus. So it is a strong nuclear force and a weak nuclear force. Question is, what are the principles which govern these forces? And just to give you an idea about how difficult this was thought to be, Freeman Dyson was one of the pioneers of quantum electrodynamics that I mentioned. He had this to say: the correct theory will not be found for the next 100 years. Okay? This was in 1960. But amazingly, the correct theory was found within 10 to 15 years. So sometimes that tells you the eminent scientists can be eminently wrong. And the principle, but there is a kind of unification of principle. That even though these are totally different phenomena, you would agree a nucleus decaying, a nucleus being held together, has absolutely nothing to do with electricity and magnetism. But it turns out that they are governed by the same principle, which is known as the gauge principle. And SUN quantum gauge theory is what describes all of these forces. And I just want to describe to you in simple language. So this I have called unification of principle. There is one single principle that is describing all these forces. So for example, We had, for the Maxwell field, you had one field F, and we wrote down those equations, and one single electric charge, right? You can have, the charge can have value +1, -1, +2, -2, but there is only one type of charge. Now, what happens if you take two types of charges, up and down? Then it turns out that the F has to become a 2 by 2 matrix. So it looks like a pretty straightforward and simple generalization. And in fact, at the classical level, it's actually a very simple and straightforward generalization. This is called the non-abelian gauge theories or Yang-Mills theories. But the principle is very similar. The equations are very, very similar to Maxwell's equations. So you have 3 charges, it becomes 3 by 3 matrix. N charges, it becomes N by N matrix. Of course, at the quantum level, these theories are actually far more complicated than quantum electrodynamics. But at least to get started, the idea is very simple. And it turns out, amazingly, this relatively minor modification that human beings did turns out to be an exact description of these. So you can have, this is because you have one charge, it's called U1, SU2. Sorry, what happened? It got kicked out of the, can you, hello? How do I, I'm not able to click on it. Yeah, okay. So electrodynamics, weak nuclear and strong nuclear, these three very distinct forces are described by the same principle with slight generalization of the notion of gauge theory, okay? So joining, now the question becomes, can we really join electromagnetic and weak forces in the way electricity and magnetism were joined together? Could the weak nuclear force be joined together with the electromagnetic force, right? You could ask this question over coffee. Then there was another eminent physicist, Wolfgang Pauli, one of the founders of quantum mechanics. He had this to say, actually when Salam was thinking about this, he said this, he had this very witty comment, let no man join together what God hath torn asunder, you know. This is a kind of a joke on when people get married in the church. They say that let no man tear asunder what God hath joined together, like when people get married. So this was his advice to Salam, and good for him, Salam didn't listen to his advice. So this is an advice to you, don't listen to eminent scientists. Think for yourself. So he actually succeeded, and together with others, electroweak unification. And there were many new ingredients, you must have heard about them in popular reading, spontaneous symmetry breaking, I won't describe them. New particles like the Higgs boson, the massive vector boson. And this is what led to the 1979 Nobel Prize of Glashow, Salam and Weinberg. And this is Abdus Salam. So another slightly poetic way of describing unification is a bit like this, that, you know, this is the temple of electromagnetism where you worship the deity of electromagnetism. And here is another temple where you worship the deity of weak nuclear force. And one day, by accident or somebody's efforts, you discover that there is a secret passageway which connects these two temples. And in fact, they are part of a big temple complex. And you are actually worshipping the same deity, electro-weak unification. So that's roughly the idea of unification, that what you think are completely distinct phenomena are now suddenly to be regarded as, it's like Trimurti, you know, they're part of the same entity. And now physicists have, this also you must have seen, what is known as the standard model, relatively really very simple set of ingredients. This is really the fundamental, our understanding of atomic structure of matter, everything in the universe that we know. Some quarks, up quarks, down quarks, etc., and some leptons, neutrinos, and photons, etc., weak vector bosons, and so on, massive vector bosons, and the Higgs boson. Together, this table is sufficient to describe literally everything from nuclear reactions, nuclear reactors, what is happening inside the sun, what is happening in your iPhone, semiconductors, literally everything in great detail can be described using these equations, which are very similar to Maxwell's equations that you wrote down. So I'm now going to switch to my other theme. So if there are any questions from the students, please feel free to ask. Or should we take the questions in the end? As you prefer. Okay. Yeah, maybe, we can keep the shorter questions now and longer questions later.
Okay, so whenever people are trying to unify different theories, so how, and they know from the experiments how these particles or interactions behave. So how do they pick up the right mathematical formulation or framework which might explain the different interactions and the phenomenon?
Yeah, I mean, if I had a answer to that question, I would have several Nobel Prizes.
But you studied your focus is on unifications.
So I will tell you how my generation is doing it towards the end of the talk. I mean, usually it doesn't start by looking at the data, but you need some bigger idea, which is actually not part of the data. Otherwise, like Maxwell, right? He had to write down some equations. He had to invent a whole mathematical structure to put known laws into some framework. And then he discovered some new phenomena. So usually it's a process of struggling with what we know and imagining what could be. But it's a very constrained kind of imagination. It's not like an imagination of a painter where you can paint whatever you want. You have to paint what is consistent with what you know. And that's a much harder kind of creativity. And there is no simple answer to your question.
Thank you, sir.
Just a quick question. You mentioned the cases where you have 2x2 matrix and a 3x3 matrix. Is there a natural way to extend it to n cross n?
Yes,
matrix?
that's what I meant by SUN gauge theories.
Okay.
If you do n cross n matrices, it becomes SUN gauge theories. And as we will see in the end, SUN gauge theories, in a completely unbelievable twist of intellectual development, turns out to be related to gravity, as I will come back.
Thank you.
So now I want to switch to the other idea of unification. This is a beautiful location. This is ICTP. This is where we are located in the beautiful Adriatico, next to the Adriatico Sea. It's another bioreserve. There's a very nice palace over there. It's an Abdus Salam International Center. We just celebrated 60 years, much like IIT Delhi. In 1964, we were founded. And now I want to switch to this notion of joining forces to unite the world. And I want to tell you a bit about ICTP because it has very strong connections with the Indian scientific community over the years. And I think I'm going to discuss. I had the opportunity to meet with you last time. Tomorrow also I'll be meeting with the DST secretaries and MOs. And we are really looking to strengthening and the PSA to strengthen the collaboration between India and ICTP. As you know, last year the Italian ministers visited in April. So there is a strong interest in increasing the collaboration also at the national level. So ICTP was founded. It's basically international cooperation for and through science. It's a UN organization. So we are not actually Italian. We are located in Italy, but we are a UN organization. We are governed by a tripartite agreement between the Italy, International Atomic Energy Agency, and UNESCO. Robert Oppenheimer was the first chairman of our council, who helped to formulate the vision for ICTP for the coming years. And the idea is to overcome the barriers of gender, ethnicity, and also very importantly, as you know, geography and economics, to make science globally available, to make advances in science available to everyone, irrespective of where they are. And some of them, for example, here is Professor Ashok Sen, who got the Dirac Medal, a very prestigious medal from ICTP, one of our close colleagues from India, a string theorist. This is actually Juan Maldacena, he's from Argentina, also a very eminent Dirac medalist himself. So just to give you an idea about the scope of ICTP, we have had more than 200,000 scientific visits from basically every nation in the world. About 67% are what we have been calling developing countries, and I'll come to that because I think India is, or China is not, but this was the denomination we used to use in the past. About 30% are women, and we have had an enormous impact in building scientific communities around the world, contributions to many breakthroughs in science, including to 5 Nobel Prizes. And every year we have about 6,000 scientists coming for very top level conferences, 60 conferences. So the idea is that it's an international hub for science. It has a unique mission with this combining excellence at the frontiers of science with a global inclusion, making it available to everyone, and international cooperation through science. This was the vision of Salam, that scientific thought is the common heritage and creation of all humankind. I should remove that additional creation. And ICTP has been successful in the last 60 years, and this was recognized at the United Nations last year. I had the opportunity to present ICTP to the member states of the United Nations at a high-level meeting. So this is ICTP at the United Nations. Actually, this is Professor Duncan Haldane, a Nobel laureate. This is the Ambassador of Italy. But I want to tell you about stories of 3 people who were present. This is Raji. He came from Ethiopia, a small town village in Ethiopia, from a modest family. But he was a brilliant student in the university, and the teacher recognized that he wants to become a physicist. So he said that if you want to do physics, you should go to ICTP. So ever since he joined undergraduate studies, he had been dreaming of coming to ICTP. He came to ICTP actually. He did a very nice project with me, as it turned out, a summer project. And then he went to do his PhD at MIT. So now this opportunity was made available to him by ICTP. This is Estelle. She's from Cameroon. She did her PhD at ICTP. She was in the 3ST system. Now she's a scientist at Perimeter Institute, and now she's become an entrepreneur and she's starting her own company. This is Minister Rapapa. He was a student of my colleague here, Andres Candelo. He has now become a minister in Lesotho, Minister of Science. So this is the kind of impact that ICTP has had really in different countries and at people of different, in different parts of their life. And we have, not only do we organize activities at 3ST, but all over the world. With ICTP in India, I want to mention this. I mean, you have, to some of my colleagues who are present, that close to 12,000 Indian scientists have been to ICTP and fully funded by ICTP. And now we are looking to strengthen this with a somewhat different model, looking to the future and taking into account the development that has happened within India. And we are looking at agreements with the DST, MOS, and several other institutes. But I just want to tell you from my own personal experience, when I returned to India, and I was working in India for many years at the Tata Institute of Fundamental Research, and we organized a major international conference, Strings 2001, and many luminaries like David Gross, Edward Witten, Stephen Hawking, they came. And we were, of course, short of money. And ICTP immediately gave us 30,000 to host this major conference in India. So even in that role, ICTP has been playing a very important role. And I believe in the future, it will play this important role even more to help internationalize Indian science and to help nurture the research environment in India. But now as an equal partnership, taking into account the strong and vibrant scientific community that already exists in India. And this is something that I plan to discuss also with my colleagues. So now let's go back to the first theme. Now, so far I've told you kind of the history of unification and the history of ICTP. Now let's look to the future. Looking to the future, if I've been talking about forces of nature, evidently I have left out the most important force that everybody knows in high school, which is the force of gravity, the first force to be formulated mathematically. And Newton's laws of gravitation, which he wrote down more than 300 years ago, continue to predict planetary motion and how rockets move in great precision. Now, question is, how does gravity fit in the scheme of things? This is clearly a very important question. Can the force of gravity be unified by other forces? Right? And it turns out that gravity actually doesn't fit in this framework at all. This, right, you ask this SUN gauge theory. Gravity behaves in a very different way. And so before we get there, I want to describe to you how actually gravity needs to be unified first, before we even ask this question. And this has to do with relativity of time. Okay? And which led to another kind of unification, namely unification between space and time. You see, space is space, right? I can go this way, I can go that way, I can go up and down. There are three directions. And time, okay, time is running. What is the connection? They seem like, again, two completely different aspects of our reality. But Einstein realized that they have to be combined together for a very simple reason, and as I will illustrate, I will explain now, that relativity of time, what does it mean? It means that, see, Newton thought that everybody's clocks runs the same way. But as a matter of fact, moving clocks run slower. Okay, this might look like a very outrageous statement, but it depends, Einstein realized, about how you define clock. So one simple way to define a clock would be to take a beam of light and make it bounce up and down. And when it comes down one way, that's 1 unit of time. But there is a very fundamental fact that speed of light is constant in all frames. If you combine these two things together, it automatically follows that space and time have to be unified in one framework. And why? You can see this in this nice video that was made by World Science. See, this is a moving clock. And in the moving clock, the light ray has to travel longer distance. So just by using Pythagoras theorem, this is the kind of thing that I torture my son with. With Pythagoras theorem, you can actually derive Lorentz transformation, and E is equal to mc square. It's a very simple calculation. Once you understand, this is very, very counterintuitive notion that the speed of light is constant in all frames, right? See, if you throw a cricket ball and at 50 kilometers and you get on a motorcycle, you can catch the cricket ball because if you go at 50 kilometers. So the speed of the cricket ball looks different whether you're on a motorcycle or you're on the ground. But that's not true for the speed of light. And it's a fact that is very counterintuitive. And that fact is at the basis of all the counterintuitive things that you see in relativity. But once you accept that, the mathematics is simple, everything follows. Okay? And what that means is that there is a universal speed limit that you cannot, this is the universal speed limit. It's not in kilometers, okay? It's in terameters. So it's roughly about 1 terameter per hour or 300,000 kilometers per second. Nothing can travel faster than the speed of light. And it has two dramatic consequences: gravity waves and black holes. And both of these are really at the frontiers of research. Gravity waves, India LIGO experiment is actually, India is part of this major experiment, LIGO. It's going to go on. It's going to start in India in a few years. And I want to now explain to you how this connects to gravity and how this will connect to our general idea of unification and some of the work that my generation has been doing, including myself. So there is a fundamental logical inconsistency between just the two slides that I showed you. Newton's law of gravitation, do you remember from high school days? Right? What does it say? Yeah, m1, m2 divided by r square. There is no time there, right? So the force between the sun and earth is mass of the sun, mass of the earth divided by the distance between the two. Now my question is, suppose the sun disappears now, what will happen? When will we come to know about it? Instantaneously, right? If the sun disappears, according to Newton, instantaneously, because the force of gravity acts instantaneously. But this is logically inconsistent with what I just told you, with nothing can travel faster than the speed of light. So what's going on? According to Einstein, earliest in 8 minutes, maybe even slower, because light takes that much time. So this really bothered Einstein, and it took him 10 years, 11 years to really come to grips with it. And this led to unification of gravity, space, and time. Okay, so I'm just talking about all kinds of unification, but it's not some random unification. It is really forced upon you. You have to, if you want a logically consistent framework, you cannot sleep at night peacefully, saying that, oh, speed limit of light is this, but okay, gravity acts instantaneously. In fact, actually, Newton was very bothered by this. It's an interesting piece of history. Newton actually, there are a couple of quotes, I don't maybe remember it exactly, but he said that nobody in a possession of his faculty of thought would believe in this absurd proposition that if I wave my hand, the moon gets affected, right? Because that's what Newton's law says. So Newton actually understood that there was something wrong with his assumption. How could something action at a distance instantaneously? But he wisely kind of made a research tactical decision to postpone this resolution of this puzzle for future, because it took 300 years, So he said, okay, I don't really understand how to resolve this, but given these laws, planetary motions I can predict. Okay, so it was, Newton being Newton, of course, understood the flaws in his own theory, but it was a very deep and difficult flaw, which he would not have been able to resolve in those days without all the knowledge that followed. So this leads to unification of gravity and space-time. And gravity then, now in Einstein's conception, is seen as a curvature of space-time. And it sounds like a very fancy words, but it's not that fancy actually. So suppose you take a sphere, hemisphere, like Earth, and you start at equator. Start walking towards north, okay? And somebody starts walking at north, and we are just following our nose straight up to north. Surprisingly, after a few days, few months, you'll meet each other at the North Pole. And then you'll be surprised. You'll say, wow, maybe we are attracted to each other. There is some mysterious force of love. I don't know what is acting between us. But there is actually no force acting between you. It's simply that you're moving in a curved geometry. If you were on a flat plane, you will never meet. Two parallel lines never meet. This is Euclid's fifth postulate. It is violated on a curved manifold. So this is known as Riemannian geometry. And generalization of this, including time as one of the dimensions, basically leads to gravity. Okay, so it's not, once you understand again the basic concepts, the mathematics can be worked out, but the basic concept is this. So general relativity, more generalized notion of time, that's why it's called general theory of relativity of time. And it is a generalization of Newton's law of gravity. So at low speeds, it reduces to Newton's theory. But if the speed of light really becomes infinite, then it reduces to Newton's law of gravity. But it predicts gravity waves, and it predicts black holes. So gravity waves is predicted. It's clear to you, because if the sun disappears, gravity wave has to be a consequence of general relativity, because general relativity was in a way invented to solve that problem. But then it had a consequence that Einstein did not anticipate. And in fact, he fought in a way against it. So we know that there is an escape velocity. If you throw a stone, it goes and falls somewhere. If you throw it fast enough, it will start going around like a satellite. And if you shoot it up at the escape velocity, it will escape. Otherwise, it will keep falling down. And every planet has a certain escape velocity. On Earth, it's a bit less than 1 kilometer per second. So the rocket goes a little faster than 1 kilometer per second, and then it escapes. Now imagine that you make the Earth very, very dense. As you become denser and denser and denser, it becomes, escape velocity becomes bigger. So 1 kilometer, 2 kilometers. What happens if it becomes 300,000 kilometers per second? Then you have the universal speed limit. And what happens then? Okay, the question is what happens, right? You can certainly, you can imagine compactifying the sun into about a 3-kilometer radius. The entire mass of the sun, if you squeeze it into 3 kilometers, this escape velocity will be about the speed of light. Then you have a black hole. That's called a black hole because light also cannot escape this star and it just should fall. Everything should fall. So what happens? So there is something called an event horizon. So there is a more precise mathematical definition of a black hole, which I will not describe. But the main idea is something like this. So this is artist's impression of a black hole. But it's literally a hole in space. In fact, I could be walking through the event horizon of a black hole. So what is so special? So locally, there is no difference. It looks like normal space-time. I'm just going through, crossing a black hole. Or you might have actually crossed a black hole when you came to this talk. Okay? A black hole event horizon. The difference is that there is a more precise notion of definition. It's called a stationary null surface. What that means is that it is both, it's not moving in time, but it's actually moving at the speed of light. And it somewhat sounds a bit counterintuitive. But the main consequence of that is that it's a one-way surface. Once you cross it, you can never go back. So now even if you're bored and you want to go out and leave this lecture room, you cannot leave. If this was a black hole, okay? Once you're inside, you cannot go out. Something very terrible will happen to you in the future, but you cannot go out. You will meet some singularity. But you can fall into the black hole, but you cannot come out. So this actually formalizes, there is a more mathematical way of understanding what is a black hole. And it roughly corresponds to this idea that nothing can really go faster than the speed of light. And if the mass is large enough, you cannot escape beyond this horizon. So this is the event horizon, which even light cannot escape. So it really looks black. Now, some of these ideas we read in popular books and we sort of start believing in them. But you don't know actually what kind of intellectual struggle underlies this. I mean, Einstein immediately wrote a wrong paper, actually. Einstein wrote a wrong paper proving why the Schwarzschild singularity, what he called a singularity, is actually not a singularity, cannot exist in a theory of nature. And he was completely wrong about it. It took almost 50 years for the community to accept that this could be real. And it took another 50 years to really discover it in a convincing way. And this is the most spectacular discovery, one of the most spectacular discoveries of this century. Merger of two black holes which happened 1 billion years ago. And this is a rendering by the LIGO experiment. So I'm just going to run it. It's an enormous energy because when two black holes merge, the original masses were like M1 plus M2. The final mass is much smaller than M1 plus M2. So all the mass has to be emitted in a burst of energy using mc squared, where c is this enormous speed of light. So it's an energy that is unbelievably large. You cannot imagine, it's much larger than the energy of all the stars for that fraction of a second. But it is all in gravitational waves. Nothing is visible. And this is what happens. And these little dots are actually stars around these black holes. This is how it will look to you if you were nearby the black holes. Because as the black holes move, the gravitational field changes. And these, they get deflected. This is called gravitational redshift. So the stars behind, so it will go and collapse. And this LIGO experiment is basically a laser beam, 4 kilometers long. So when a gravitational wave passes, it sort of jiggles it a bit, shakes it a bit. And then the interference pattern changes. This is how you measure it. And it's quite, if you think about it, it's really spectacular. It's quite amusing that, we, after all, are descendants of monkeys, we human beings. And then they set up this experiment, put this up, a billion years after this black hole had actually merged. And by coincidence, this wave was passing and we detected it. Using both these principles that I've told you of quantum mechanics, of lasers, and general theory of relativity. So that tells us we need to combine quantum mechanics with general theory of relativity. And this is the final frontier of unification. which is what my generation has been engaged in for the more than last 50 years. And it's one of the most exciting intellectual challenges, but also one of the most difficult ones. Unification has been an inspiring guiding principle. Electroweak unification, as we saw, of Abdus Salam and others, was a very important milestone. But in 21st century, can we unify gravity with other forces? That's the question. And as I told you, gravitons, which are the quantum of the gravitational wave, they for some reason behave very differently. They don't fit in this framework of gauge theories. If there were some SUN gauge theory, we would be done, and there is nothing to be worried about. But they don't. These are not the laws they follow. And their characteristic distance scale where this kind of phenomena will become important is Planck length, which is trillion times smaller than the atomic nucleus. So you might say, okay, this looks like some very exotic problem. And even if you can think about it if you like, but how can you even make progress? Okay, how can you be sure that you're on the right track? So it's a challenge. And this is where string theory comes into picture, which is the field of my research. Why so many top scientists are excited about string theory is that while in normal quantum mechanics and quantum field theory, gravity is very problematic and is impossible. When you think, and by normal quantum mechanics, you mean in terms of point particles. So particles are coming and striking and interacting with each other. If you replace that with strings, suddenly gravity not only becomes possible, but it becomes inevitable. You cannot switch it off. String theory always contains gravity. This is why people are excited, that it's a problem that we think is hard to solve. And here is this framework of string theory where it automatically gets forced upon you. So here is like what I mean by point particles. You know, this is an electron going like that. It meets another electron, then it emits a photon, right? These are called Feynman diagrams. But the gravitons have different Feynman diagrams. And there is a big difference between these two diagrams, which I won't explain. But these diagrams give you infinite answers. So it's a bit like saying that the force of gravity between Earth and Sun, which is described by Newton's law, when you include quantum corrections, it's infinite, which is clearly nonsense, right? So there is something wrong when we try to put quantum mechanics together with general relativity. And what saves you is that in string theory, because graviton and photon are excitations of the same thing, if the string is like a violin string, so one note sounds like a graviton, like sa is like graviton and re is like a photon, roughly speaking. And therefore, they are kind of unified to begin with. Secondly, if you now draw, one string is coming in, it meets with another string and it joins together and it goes. This is how the diagram looks. And you see in this diagram, there are no pointy things. This is a graph, whereas this is a manifold, okay, in a more precise way. Here there is nothing, everything is smooth. And it's because of that there is no divergence, or there is no infinities in string theory. This is really the fundamental reason why string theory are exciting. Why there are no divergences in string theory. And moreover, two things which look very different are unified. So it's a bit like you had two different kind of Lego blocks. I gave you the analogy of a temple, but it's another analogy would be you had a mechano and you had the Lego blocks. And one day you discover some new screws which can actually couple the two things. And then you are excited because then you can build bigger structures. Okay? But now the question comes, how can you be sure that you're not fantasizing about your theory? And this is where the work of Hawking comes into play. And this is also my own work is involved in this is quantum black holes. So what happens if you study the quantum properties of black hole? And what Hawking discovered is that the black hole actually is not really black, but it's little like a piece of coal or a piece of hot metal, and some radiation is coming out of it. But you know that when something is hot, there is something called entropy. It is really made up of some bits, right? Like this room is hot. And the way we understand why this room is hot is that because there are little atoms knocking around. And the faster the atoms are moving, the more is the temperature in this room. So the motion of the atoms, the bits of this gas, explain to you why the gas is hot. And that's called entropy. So, but what Hawking discovered was really, in a way, shocking, that the bits of a black hole follow an area law, meaning they're all stuck at the horizon of the black hole. So imagine it's like everything that is happening in this room is described in terms of what is happening on the walls, right? This is not what happens in normal physics. In normal physics, to describe what is happening in this room, like there is a chair there, there is this there, I will need to give information in terms of bits which are scaling with the volume and not with the walls of the black. But this actually what happens for a black hole. And nobody really understood this, how this is supposed to make sense. So unlike normal matter, black hole has this area law. It's like a hologram. The surface of the black hole is like a hologram. It's like a film which is taking an image of everything, three-dimensional thing that is happening inside. So that's the word holography, where it comes from. And what people discovered is that this hologram is actually described by this SUN gauge theory. So this is a complete full circle of an intellectual development. And this was actually a very shocking development. And this happened during my lifetime in the last 20 years. And I don't think it is fully understood yet. This is going to take us 50 years to understand what it means. Because imagine what it means. It means that a theory in which nothing is falling, because in theory of gauge theory, like electromagnetism, there is no gravity and things don't fall down, is equivalent to a theory in which things are falling, in which there is gravity. So the equivalence between gauge theory and string theory was one very big surprise to that was uncovered in the last 20 years. And somehow the gauge theory knows all about. Okay, I'll speed up now. This brings me to, I will describe very quickly my work in this context of quantum black holes. The question is, given the fact that you have so many qubits on the surface of a black hole, can you count how many qubits are there? Suppose I give you a black hole. Can you tell me whether the black hole has 500 qubits or 357 qubits? Can you do a calculation in your theory? If you claim to have a complete theory, you should be able to calculate the number of qubits. This problem actually turns out to be related very closely to some very beautiful mathematics that Ramanujan invented. And his problem was very simple. Let me give you that problem. Suppose I give you a number, like 3. And I tell you, write me the number of partitions. Like how many ways can you write 3? Like 1 plus 1 plus 1, 1 plus 2. Maybe as I tell you that I give you 2 colors. So you can write it as all green or red, some green, some red. So P of 3 with 2 colors is 10. Okay, that's called the partition of the integer n with so many colors. Now you can switch off the light. This is the movie clip from the movie The Man Who Knew Infinity about Ramanujan. This is where Ramanujan goes to meet Major McMahon, who is a very famous combinatorial mathematician, also kind of a bit racist, as you will see from the... So he sort of has kind of very dismissive attitude towards Ramanujan, you know. So...
enter at your own risk.
Volume.
Ah, I've been waiting for you. Square root of 58,639. Now.
242.
242 what?
0.1549090.
Yes, child's play. Try me.
Go on.
Same number squared.
3,438,532,321. Ah, thrashed you. Combinatorics, that's what I do. Glorified dice throwing. Bloody nerve of you both. You fail on primes and you think you can just turn around and crack partitions. Can't be done, I'm telling you. Especially not by you.
It can. And I will.
No, I will. By hand. by slow and painful addition, and then you can be absolutely certain that whatever formula you two can dream up will be quite wrong. Then you can crawl back under whatever rock you came from in India, and we can put to bed this charade of yours, Hardy. Now, how high do I have to go?
P of 200 should do. I really can do it.
So basically, he's asking him to do partition of 200. Okay, and you can imagine, you can write 1 plus 1 plus 1 200 times, 1 plus 1 plus 1, 198, and so on. If you try writing it down by hand, you will have to work for days. But Hardy and Ramanujan had this beautiful formula. This is with 24 integers, 24 colors, partitions of an integer. And this is some Bessel function, these are some Kloosterman phases, it's some number theoretic phases. But it's an exact formula, it's a conversion series. And all that you have to do is plug in. You know how the Bessel function is. You just plug in 2 minutes you can calculate this on a calculator. So you don't need to do painful addition. Beautiful exact formula, and it's useful, it turns out, for counting the number of qubits of a black hole. But not exactly this formula, but a generalization of this formula. And this is the, sort of the, what is it called? Yeah. The showdown when Ramanujan goes to meet him.
Well, here we are, P of 200, the moment of truth. I was stationed in Madras once. Yeah. Well, you first. What has your formula given you?
3,972,998 million.
My God. You're close. Within 2%. Well, I'll be damned.
Major McMahon, may I introduce you to Mr. Ramanujan?
So now I will have maybe another 5-10 minutes, right? Okay. So it turns out that in some simpler models with some additional symmetries, you can actually count the number of qubits of a black hole exactly. But not only that, you can actually calculate them gravitationally independently by using very different methods, using what is known as path integrals. Again, a very difficult calculation on both sides. And when you put it together, you find like 512 on one side and 512 on the other side. Again, very highly non-trivial check that very, very tight internal consistency of a theory of gravity where gauge theory is equal to string theory. In precise agreement with Hardy, an analog of the Hardy-Ramanujan formula. So what is even surprising is that somehow gravitational theory knows about an integer. The horizon of a black hole actually has information about some number theoretic properties. So this is in a way not surprising because it's a kind of quantization of space-time. It's a quantum space-time. And there have been several such very highly non-trivial tests of this holographic duality, which is why the scientists are confident that we can actually make progress, even though there is no direct experiment forthcoming anytime soon. And therefore, we continue this quest for unification of gravity with quantum theory, with fascinating connections between quantum black holes, gauge theory and string theory. Now there is also very fascinating connections with entanglement and quantum space-time. And there is a very nice quote of Einstein that I really like. It's an encouragement and also a warning. He says that the successful attempt to derive delicate laws of nature along a purely mental path by following a belief in the formal unity of the structure of reality encourages continuation in this speculative direction, the dangers of which everyone who dares to follow it must vividly keep in mind. Because you can be led astray, so you have to be prepared for that. But now, I'll come back to now my second theme, the future of ICTP in a way, or the future of uniting the world through by joining hands. What comes out of this story of black holes is that unity of science, you see, The concepts that were created by somebody like Riemann about Riemannian geometry, and who was in Germany, then Stephen Hawking, who was in the UK, and Ramanujan, who is from India, in completely different fields, there are unexpected links which are totally critical for any breakthroughs and any new developments to happen. So if we had just shut down, if Germany had closed their doors or had decided to, or India was not, Ramanujan didn't have the opportunity, some of these advances would not have happened. And this is why the curiosity-driven science is so important. And this is a point that always comes up when I'm talking also to policymakers or funding agencies, that why should we invest in curiosity-driven science? Why don't we just directly invest in technology, which is what a developing country like India needs? Because fundamental science actually motivates excellence. Young people are excited by these fundamental questions. It helps to attract talent. As I saw that science is a whole, it's a very organic object. You cannot just say that I want this part and I don't want the other part. So you need somebody making truly disruptive technologies as possible. For example, neural networks which really underlie AI were kind of formulated by a statistical physicist with thinking about somewhat motivations coming from but of course you need a healthy balance between pure science and applied science. You cannot invest all theory and experiment. But one advantage is that theory is cheap. For theorists, you just need to give a pen and pencil, but maybe now a computer or maybe computing power, which can be expensive. Okay, so fundamental science is the driver of technology. Very important to appreciate the essential unity of science for national policies and public investment. Without quantum mechanics, really understanding, you cannot have quantum technologies. You can have, but you will only be a consumer of quantum technology. You'll never create quantum technologies. So if you want to make in India, you have to first invent in India, or innovate in India, or discover in India. Without basic physics, you cannot have artificial intelligence, because as I told you, neural networks actually came out of basic physics. Overemphasis on technology is short-sighted. So I, of course, understand, having lived in India, how big are the problems facing our country, from primary education to clean water. So it would be, of course, silly to say that a government should invest in pure science at the exclusion of everything. But it's also would be short-sighted if we not do enough for pure science and trying to find the right balance. There is a nice quote of Euclid. When Euclid was asked by Emperor Ptolemy to teach him geometry, he found it too hard. So he said, okay, Euclid, can you please simplify? Can you make it easy? And he is supposed to have said that there is no royal shortcut to geometry. And I think one can say the same thing to policymakers, that there is really no royal shortcut to technology. You have to invest and build scientific community in your country, while at the same time building technological competence. We don't want the next Ramanujan. Ramanujan was almost lost. I mean, his genius would have gone unnoticed if it was not for a lucky accident with Hardy, who was shown in that movie. If there was some other mathematician, actually several mathematicians actually ignored Ramanujan's letters to them. He was really fortunate that this collaboration happened between him and Hardy. And Hardy was, of course, magnanimous enough to understand that Ramanujan was even a greater mathematician than himself. So how to create conditions to nurture the next Ramanujan? And here I want to go back to the theme of ICTP. There are two actually visions, in a way, of Bhabha, which has dominated the way scientific institutions have been set up in India, driven by Bhabha's vision that we need a strong scientific community in India. And this was, of course, I completely understand this and I completely agree with this, which is why, I mean, I studied for many years in the US, but I really wanted to come home to India. And so I came back to India. I was working in Tata Institute of Fundamental Research, founded by Bhabha, for several years, for more than a decade. So I'm very familiar with the motivations. And I think one can safely say that the ambitious goals which Bhabha's generation had set for themselves have largely been accomplished in India. The competing vision was that of Salam, International Hub for Science. And actually, Salam was led to it in a somewhat roundabout way, because actually in Pakistan, he did not find the same kind of support that Jawaharlal Nehru gave Bhabha. So he was forced to leave his home country, and that really bothered him. He was not as fortunate in a way. And I can sort of identify with Salam because he also came from a small village in Pakistan and really wanted to go back to his home country. But the times were very different in his time and in my time. For me, it was easier to come back to India. For him, it was impossible. Essentially, he had to give up, make a choice between physics and being in Pakistan. And that led him to... sometimes people say that, okay, these are two competing visions. But when I became the director, I thought a bit about it because I believe that they are actually complementary to each other and not competing with each other. Because even India now is at a very different stage of its development. It has a very strong community. It has very strong financial abilities. But still, for internationalization of science, it remains, because as we saw, science is fundamentally international. What is happening in other corner of the world is important. Talking to people is important. Global platform for global challenges. So, for example, some of the challenges like cyclones or pandemics do not respect national boundaries or political divisions. So we need a platform where we can engage together. And ICTP does precisely that. We being a UN organization, we are a place where in the 1964, plasma physicists from Soviet Union could talk to a plasma physicist from the United States. Or today, we hold climate workshops, monsoon workshops, where all scientists from this region, Indian subcontinent or China, can come together and discuss with each other science. Because after all, a heat wave in Delhi doesn't stop in Delhi. I mean, it doesn't originate in Delhi. So you cannot, or if a cyclone is happening, it's going to affect Bangladesh and Bengal equally. And to think in terms of national boundaries really makes no sense. And we need a platform where this discussion is possible. So that is my view for the ICTP of the future. The vision for the ICTP of the future is we have identified a number of strategic priorities. One of them is the International Consortium for Scientific Computing, because things like climate or also materials, quantum materials, any kind of computing. Now we saw AlphaFold, protein folding problem. More and more computing is going to be the essential for science. And if open science is our goal, then open access to computing in some form or the other becomes essential. And that is where ICTP with its unique UN mandate can play a very important role in collaboration with our partners in India and elsewhere. There is a large knowledge divide when it comes to AI already between, let's say, Bay Area and Europe, even between Bay Area and Europe. So I think this is quite an unstable and dangerous situation. And of course, ICTP cannot address these big problems, but we can do at a level of a scientific institution to create at least a consortium for scientific computing. So it's really an obligation of ICTP. And this is where we look for partnerships. International Science Alliance is something that I have been thinking about. We have signed a number of agreements, substantial ones with IBM, Quantinuum, or supercomputing facilities in Italy, Switzerland, or foundations like Simon's Foundation, and countries like South Africa, Brazil, Kuwait, and hopefully now India in coming months. So we look at ICTP to unite the world together through science and for science as a kind of lighthouse for science. This is an image that I like very much. This is the Faro della Vittoria, the lighthouse of victory. It's actually a lighthouse in Trieste, where ICTP is located. You can see ICTP is in the background over there. So we imagine that science can be, of course, it would be naive to imagine that science can help in solving difficult political problems. But what science can do is actually, it's a common language that everybody understands. It can bring people together. So it can facilitate dialogue, which is something which ICTP has been doing and can do even more in the coming years. So I will stop here. Thank you.
Thank you for a brilliant talk. I know I can ask you this question since we go back 46 years. You're, apart from being a brilliant physicist, you're both a rationalist and a violin player. And so the lighter question is, would you have gone into string theory if you hadn't been a violin player? The deeper question, and I want you to answer this not for myself, but for people around here, is that you said the theory is cheap. How do you guard how do we guard this world against crackpots and political operators who have an answer to every unasked question?
Now, first of all, I should say it's really great pleasure to see my good friend, Professor Sanjeev Prasad, who is in computer science here. And as he said, we go back 46 years. We know each other's secrets, let's say. We were undergraduates together in IIT. So I think, I mean, the questions that you asked, I mean, also about rationalism and about the keeping true to the real science as opposed to crackpot science. Tomorrow I'm giving a talk actually related to this topic. And actually in Bombay on the National Science Day, I'm giving this talk on scientific temper in the age of unreason. That is the title of my talk. And it's a very important question to really, I believe, that just like Thomas Paine had this famous age of reason, and there were all these ideals of enlightenment that we all believe in doing science, which are slowly getting eroded and it's surprising. I mean, despite the spectacular progress of science on one hand, there is spectacular opposition to science. And there is this anti-science attitude, anti-vaccine attitude, climate change denial. I mean, basically, and this is a very interesting social phenomena which we as scientists must address. And this is a topic of the discussion in my talk. But there's a long answer, but what I can say is that I think we have to be really empathetic to the understanding why are people driven to this kind of an anti-science attitude. There are issues where science can be criticized, like the elitism of science can be criticized. There are issues about science that can be criticized. But we should be really uncompromising against this kind of fluffy new age criticism of science. And we must make clear what science needs to change in the methodology of science, but what must be accepted about scientific truth, which is non-negotiable. And I think this is a difficult discourse, but I think this is a challenge for our generation. And I think just like the Enlightenment philosophers and thinkers had to fight against this is the challenge for our generation, or your generation, to really emphasize the scientific method. It's not perfect, but it's the best thing that we have, okay? And if we give up on the notion of objective truth and start believing in alternate facts and every crackpot theory that claims to be true, then society as a whole is on a very dangerous course, and which can have really devastating consequences. It's not some abstract philosophical discussion for a cafe, you know. It is something serious, and this is the topic of my talk tomorrow and in Bombay.
Hello, sir. Thank you for this fascinating presentation. My name is Janit Jain. I am BTech final year student in electrical department. My question is like on photonic clock, that it seems to be fundamentally wrong because it ignores that the slits are made of atom, and if photon is hitting atom, then the atom don't know where the photon come from. So if it is going and if it is reflecting, then it is going to, then photon should go back. And another thing is it is not considering that atom is taking photon and electron jumping and coming back. It requires time, but we are using photon clock, so we can't consider time in that case. So how the photon clock is fundamentally using in our framework, or it is just constraint of the overall the theory?
No, I mean, the idea is that you want to define time in terms of time light takes to go from point A to point B. That's how you want to define a clock, right? There are many ways you can define a clock. One way to define a clock is that I have a gun and I shoot it at 100 kilometers an hour or per second, then 10 meters, 1 meter in a second. Suppose this is how fast the bullet goes. Then we know that 1 meter is equal to 1 second. That's all. There is nothing more complicated to that photon clock.
And how the photon,
As the interaction of the photon and the atom is not important here. What is important is how much distance does the photon travel, right? For defining the time, see, velocity is equal to distance divided by time. So either you can define distance or you can define time if you know the velocity. And it doesn't matter which one you choose.
Yeah, but
maybe we can discuss this afterwards. Okay.
Okay. One question, sir. You have also worked at CNRS, and the work and you have been you have spent longer time at ICTP. But personally, looking from outside, it appears to me that ICTP does mostly theoretical work. There could be some outreach activities, but CNRS people do work in neuroscience also, climate modeling also, epidemiology, and those people are also strong in theory. They are helping other departments in solving the challenging problems. So you talked about unity in the science, unity in the people. So how could ICTP? Why doesn't ICTP work in that similar regard? Because
so why does ICTP not do experiments?
No, not experiments. Like why doesn't it helps its it has a strong.
Why doesn't it broaden like CNRS does?
Yes,
no?
yes.
So first of all, CNRS is an enormously big organization compared to ICTP, because CNRS is all of national research in France, whereas ICTP is just one institute. So ICTP is a relatively small institute, whereas CNRS is like INRF, it's of that magnitude. So therefore, it's like saying, why does an ICTP become like DST? Right? We cannot become like, the roles are different. Okay. And so it's just a question of, we would be happy if we had 20 times more money. We can do 20 other things.
Okay, sir. Thank you.
Yeah.
Yeah, thanks, Atish. It was wonderful, your talk. I think looking the number that you was showing, you was presented, were 200,000 people moving to ICTP. So I think the philosophy to have a proximity and to have the people there is one of the big force and joint force that ICTP was doing during the 60 years. So it is, are you believing that proximity should be pushed? Because sometimes now the scientists are working independently, isolated, and what is important to make
actual physical proximity.
Yeah.
Yeah. So I think we are also starting something called ICTP Global Portal, which will be ICTP Online. So we discovered during the COVID time that we can actually do many things online. And so we can actually expand our mission also online. But it's also true, and all of you who have spent time on Zoom will tell you that there is nothing that substitutes for scientific research, personal interaction. So you cannot really substitute personal interaction. That's where random ideas get created. You need to be in this. Somehow human beings don't work like this, that you sit in front of a Zoom thing and then you say, okay, let's come up with an idea. Usually it happens when you're having coffee and then you're discussing and freely associating. So I think this interaction is extremely important. And so ICTP is trying to do both, but we don't want to make it an online institute, because it's not actually, this is not how you can do science.
Okay, we can take one more question from the Dean.
Hello, sir.
There's one question here and maybe then.
So,
please go ahead. Okay.
So, sir, when you were talking about the unification, you mentioned about the temple, there is a hidden way. So, how you as a theoretical physicist think of it as that there might be a connection or there might be a link between these two different theories, like electroweak theory, as you mentioned. So it gives naturally provides the photon and weak boson and also the new particles. So how you think that there might be a something link between the two different theories, maybe another different theories like quantum gravitational?
Yeah. So it's actually that process of discovery is very non-linear, and it's like a random walk. There is no simple logical route to it. But I think the way people in his generation were thinking about it is that they were thinking about current algebras. I mean, the currents. So the fact that if you have a current, then you need a vector particle coupled to it. So it was not so unnatural to think about a vector particle that couples to the Fermi theory was already written. So I think current algebra was one route that led to this, but it was not a logical process. There was some inspired guesswork was needed, and that is not something that you can describe logically.
So, the base is basically the random theory we just give.
No, that's why we need a kind of free association and creative thinking. I mean, that's the contribution of human beings. That if it was a mechanical thing, we could give it to a computer.
Thank you, sir.
So, my small question to you. You talked about collaboration and physically collaborating, coming close and things like to do big things. But I've seen people are very protective of their ideas, right? So how do you encourage people to really collaborate? How do you drive this collaboration? What is the logic or what is the motivation, and how do you really do that?
Yeah, so I think there is a kind of a dynamic kind of collaboration, competition, which goes together, and I mean, human beings are complicated things. So, but it works. I mean, look at the CERN experiment. There are thousands of scientists working on a single goal to construct this detector. And within CERN, they have two detectors actually, ATLAS and CMS. And they are competing with each other, meaning secretly they are competing. They don't share data. Why? Because they want to have double verification. So the ATLAS group works independently, but they're collaborating. They're actually part of the same accelerator thing. So I think we do this all the time. I mean, it's not, human beings are also very collaborative. We should not overemphasize the competitive nature of human beings. We are both competitive and collaborative. And we do that all the time. I mean, in many major missions, we build bridges and we do things together. And then, of course, we do crazy things like going to war with each other. So these destructive and constructive tendencies are unfortunately part of our evolutionary baggage. But I think a place like ICTP gives a greater emphasis to this collaborative aspect, which I think one very beautiful example of that is the Sesame project, which also part of it, the discussion started in ICTP. It's a synchrotron facility in Jordan, but it is funded by Iran, Israel, Palestine, Jordan. Now, this sounds like almost news from alternative universe, from some. How can this be true? But this actually was conceived because some Israeli scientists and Iranian scientists were together, and they said, "What about a Jordanian?" So those scientists actually had a common bond. They were talking the language of physics, and they knew each other, and they were friends, and they were not separated by this, national, and that allowed. But then they were able to escalate it to the national level and create this common collaborative facility. It doesn't work perfectly. There are a lot of difficulties. For example, now Iran, because of sanctions, cannot pay their. But this happened. It looked almost unreal, but it happened in 30 years, and it's functioning in a sufficiently good way that we can be proud of it. And ICTP played a small role in it.
Okay, I'd like to thank everyone for the discussions and the questions. Now I hand it over to Olivia. Thank you.
Thank you, Professor Atish Dabholkar, for that incredibly insightful and thought-provoking talk. Also, thank you to the audience. It was a very nice discussion. Now, to express our gratitude, I now invite Professor Ashwini Agrawal to come on the stage to felicitate our speaker for a memento. I now invite Professor Shilpi Sharma, Associate Dean, Academics, Outreach and New Initiatives, to deliver the vote of thanks.
So I think some of the thanks has already been done. I would like to, I'll make it brief because I know that I'm the one between you and the refreshments. I would like to thank ANRF first for bringing this proposal to us. And our first speaker, Professor Atish, did meet the objectives of making what Dr. Shiv Kumar said, research to be cool. And of course, we are sure that this opportunity will, and this outreach activity will go a long way in fostering collaborations. I have to thank Professor Agrawal, I have to thank Professor Shiv Kumar for gracing this occasion, Abhishek and Sarthak for making this possible. Thank you so much, Professor Atish, and my outreach team who has been working to make this possible. Thank you all so much for coming.